All right, hello everyone. In this episode, we're going to talk about ring homomorphisms and factor rings. So, as we've already seen with groups, homomorphisms are essentially a special type of function defined between two algebraic structures, such that their operations are sort of preserved. So, a product of elements in the group case, right? A product of elements before applying the function is a product of elements after applying the function. Um, so let's look at how this works for rings, right? So rings have two operations. So you basically have to sort of say that both addition and multiplication are preserved, and you also have to say that the identity is preserved. So let me just write this all down. So f from R to R prime. Let me make this colon R to R prime. So these are rings is a homomorphism. I'm going to be abbreviating it to HOM. If for all x, y, and r, we have so addition is preserved, so f of x plus y. So here we add before applying the function, and then we can apply the function to both elements. We get f of x and f of y, and we add after applying the function, right? So that's what I mean saying that. And then we get a similar thing with the ring multiplication. Okay. And then we also have to say that f of 1 is 1 prime. So 1 here is the identity in R, and 1 prime is the identity in R prime, the multiplicative identity. So note that for groups, f of e equals e prime. So here e I'm using as the identity for groups. F of e equals e prime is not required in the definition, and this is because if we look at f of e times f of x, this is f of ex, which is f of x. And in the group case, right, f of x, any group element always has an inverse. So you can take inverses of f of x on both sides, and then you get f of e is the identity in the second group, right, the image group. However, in rings, we don't necessarily know that, or we most cases we don't have that. Every element here is invertible, right? That would only be the case for fields, and of course there would be non-zero elements. So that's why we have to put in the definition of a ring homomorphism that f maps the identity to the identity. Unlike in group homomorphisms, we didn't have to specify that because it's actually a property of group homomorphisms. Okay, so that's the definition. Now we look at the kernel. So the kernel of a ring homomorphism is we view it as the kernel additively, right? So what I mean by that is, okay, the kernel for groups, right, is all the elements that get mapped to the identity. But now we have two types of identities. So we look at it in terms of the additive identity, i.e. 0. So this is x and r such that f of x is equal to 0, or maybe you want to put 0 prime for 0 and r prime. But regardless, right? So this is the kernel, and this is a two-sided ideal. Okay. So remember, two-sided ideal means that this is closed under addition, and it is closed under multiplication by r on both sides. And this is true. This just follows from the homomorphism properties. Okay, so it's closed under addition because f of x plus y is equal to f of x plus f of y. So if f of x and f of y are 0, then their sum is 0. So x plus y is in the kernel. And then the multiplicative property, since one of these terms is going to be 0, that means the product is 0. That means xy is in the kernel. And so as long as one of x or y is in the kernel, xy is in the kernel. And that shows it's two-sided. Okay. And this is going to be important. I don't think I'll have time for it this video, but in the next video, because in this video I'll show that in two-sided ideals we can look at quotient rings, factor rings, as I wrote in the title. Okay. So let's just look at some more definitions. Again, a lot of these are going to be quite like group homomorphisms. So F is an isomorphism. I'm just going to brief that as iso if there is a homomorphism G. So this is going to go in the opposite direction as F, right? So F goes from R to R prime, G goes from R to R prime to R, and such that the compositions F composed with G and G composed with F are identity maps. Meaning, so let's look at G composed with F. So this is a function from R to R, because you plug something in R into F, you get R prime. Plug that into G, you get R. So this goes from R to R. So this map, if I plug in any element in R, I'm going to get that exact same element out. And similarly with F composed with G, if I plug in any element in R prime, I get the same element out. Okay? So that's the definition of an isomorphism. Now, in fact, this condition that F composed with G and G composed with F are both identity means that G is an inverse for F. Okay. So an isomorphism has a inverse, which is a homomorphism. But we can actually show that any homomorphism with an inverse, that inverse is actually also a homomorphism. So I'll just prove this as a little proposition. If F is a bijective homomorphism, so bijective is just the sort of like set theoretic term for a function. Oops, I didn't write F. If F is a bijective homomorphism, so bijection is just a function which has an inverse, then G, which I'll define to be F inverse, is a homomorphism. Okay. So let's go through this. So essentially we just have to show that G satisfies these three conditions for, but instead for elements of R prime. So let X prime and Y prime be elements of R prime. Since F is a bijection, there are, so again, a bijection between two sets, in this case R and R prime, means that there are unique elements X and Y and R such that f of X is equal to X prime and f of Y is equal to Y prime. Okay. All right. Then G of X prime plus Y prime is equal to, plugging in these identities for X prime and Y prime, we get G of f of X plus f of Y. And now, since f is a homomorphism, we know f of X plus f of Y is f of X plus Y. And since G and F are inverses, this is just X plus Y. And furthermore, we know that since f of X equals X prime, that means that X equals G of X prime. So this is G of X prime plus G of Y prime. And you can essentially prove the other conditions are similar. So this might seem like if abstract algebra is your first look at pure math, this might seem like a kind of silly thing to show. Like, okay, we've defined an isomorphism to be a homomorphism with an inverse homomorphism, and then we've just proved that if a homomorphism has an inverse, then it's also a homomorphism. Now, the reason why this is kind of important to prove is because in topology, we have bijective continuous functions with no continuous inverse. Well, with non-continuous inverse. I mean, not necessarily, but there are examples of bijective continuous functions whose inverses are non-continuous. So an example is the map from 0 to 2 pi half closed, half open into the circle S1, and the map is given by f of x equals e to the ix. So here s of 1 is considered sitting inside the complex plane, okay? And so what we're doing is we're starting with 0, e to the ix traces around the circle, and then once you get up to 2 pi, right, you're going to get infinitely close to 1 here, but never exactly reach it. The reason why this is not continuous, the reason why the inverse is not continuous is that there is a jump here around this point on S1. Your function jumps from 0 to 2 pi, so it's not the inverse is not continuous. Okay. Another similar thing that's easy to prove is that the composition of homomorphisms is a homomorphism. Okay, so if you have f going from r to r prime, and then g is going from r prime to r double prime, then g composed with f, which is a map from r to r double prime, is a homomorphism. And this is pretty easy to prove. Again, you just want to show that it satisfies these three conditions. All right. So now we're going to shift gears and look at factor rings, okay? So let M be a two-sided ideal. Okay. And we will define x congruent to y mod M to mean x minus y is in M. Equivalently, x is in y plus M, which I defined last time to be the set of y plus little m, where m ranges over all elements. And you can see that these are equivalent definitions, right? Because if x minus y is in M, then x minus y equals to some m, right? Some element in M. And so by adding y on both sides, we get x is y plus an element of M. Okay. I'm also going to be abbreviating this notation. Abbreviation where I write the triple congruence line, and then I just put an M here to show it's congruent with respect to, or mod M. Okay. All right. So the congruence mod M is an equivalence relation. So what does that mean? An equivalence relation has three properties. So an equivalence relation takes in two elements of a set and essentially tells you whether or not they're related. And so the conditions for an equivalence relation are symmetry. So we must have that any x is congruent to itself, mod M. We can see that's true because x minus x is 0, and 0 is contained in any ideal. Okay. So this is reflex, no, this is, what did I say? This might be like the I forget the words. There's like, fancy words for these conditions, but next is that if x is congruent to y and y is congruent to z, then x is congruent to z. So this is transitivity, and it just tells you that, if two elements are congruent to the same element, then they're congruent to each other. And lastly, x congruent to y means I should say implies that y is congruent to x. And this is true because if x minus y is in M, then multiplying by -1, we get y minus x is in M. And also for transitivity, I didn't really say, but if x minus y is in M and y minus z is in M, the sum of those two things is x minus z. And ideals are closed under addition, so so that shows that x is congruent to z. So the thing about equivalence relations is that they show up all over math, and they allow you to, so equivalence relations allow you to take quotients or factor spaces. In other words, if you have an equivalence relation on a set, you consider um, the set of equivalence classes where essentially you put all the elements that are congruent to each other in one box, and then a bunch of other elements which are congruent to each other in another box, and that gives you the quotient or factor space. And so we'll see that we can, given a two-sided ideal, well, we have this equivalence relation, so we can look at the factor space R, R mod M. But first, we're going to prove some more algebraic relations. So if A is an R and X is congruent to Y, then AX is congruent to AY, and XA is congruent to YA. So these conditions are this result is true because if x minus y is an M, right? So if x minus y is an element of an ideal, it's a two-sided ideal, so I can multiply by the left by A, or I can multiply on the right by A. And so those two things give you these two congruences, essentially. Now if x is congruent to y, and x prime is congruent to y prime, then we have two things. One is that we can add congruences so that x plus x prime is equal to, or is congruent to y plus y prime. This is true because the subtraction of x plus x prime minus y plus y prime is just the sum of x minus y and x prime of y, x prime minus y prime, and the sum of two elements in ideal is in the ideal again. So that's true. And x times x prime is congruent to y times y prime. Okay, so why is this true? Essentially, you sorry, I'm brain farting a little bit. You can essentially do it in steps. So since sorry, so let's say, so we have x minus y is an M, x prime minus y prime is an M. So now I know you can't just multiply these things. Oh, I see what you do. So you multiply this on the left by x prime, so you get x prime minus y x prime is an M. And then here on the right, you left multiply by y. So you get y x prime minus y prime is an M. So here we've just multiplied, which clearly preserves the fact that we're in an ideal. And then we can add these two elements. When we add these two elements, this minus yx prime and this yx prime cancel out, and you're left with x prime minus y prime, which shows the congruence. Okay. So on top of this being an equivalence relation, we also have these algebraic properties, and that's going to allow us to show that the factor space R mod M is actually a ring. Okay, so we're going to denote by x prime the coset x plus M. Okay. Note that if y is in x prime, or sorry, I should be saying x bar here, x bar. So note that if y is an x bar, so y is equal to x plus little m for some m and m. This is an element of m. Then the class corresponding to y, right? So y bar, which is the coset y plus m, is so this is the set of y plus m prime, where m prime is an m. And so since y is equal to x plus m, this is the set of x plus m prime, where m prime is an m. And this m plus m prime is going to again be in M. So this shows that this is, in fact, X bar. Okay. So essentially cosets we can denote by a single variable, which is called, so X or Y are representatives for the for the coset. Okay. And essentially what this is saying is that if you pick some representative x bar, then for any other element in x bar, it's a representative for the same coset. Okay. Okay. So in other words, x bar equals y bar precisely when x and y are congruent, mod y, or mod m. Okay. So now we're going to let R bar be the factor space R mod m, which consists of the cosets x bar, where x ranges over elements of R. And so obviously, for each R, we're not going to have a necessarily unique coset, right? So if I take x and y and they differ by an element of m, then they are going to have the same coset. But this map is surjective, right? Any coset has some representative, which is an element of R. Now, since R plus and m plus are, well, abelian groups with m plus being a subgroup of R plus, then R bar has a structure of an abelian group because we've already studied, right, quotient or factor groups, right? So this is just a factor group, right? So we already know that R bar with the addition here, so the addition, the actual operation of addition of cosets is given by x bar plus y bar equals x plus y bar, right? Or in other words, x plus m plus y plus m is equal to x plus y plus m, right? These are just two ways of looking at it. I mean, this is just different notation, but so yeah. So we already know that this space has some algebraic structure. So now what we want to do is define a multiplication on it and turn this thing into a ring. Okay. So that's what we're going to do. We're going to define the product of two cosets x bar and y bar to be the coset represented by x, y. So now there's a problem with doing this, and the problem is that we have to check that um, that this coset does not depend on which x and y we choose to be representing these cosets. So if x prime is an x bar and y prime is an y bar, we must show that x prime y prime is an xy bar. And essentially this is nothing more than um, showing that, should I say, uh, this is the same thing as this condition here, okay, where we can multiply congruences. So in other words, we have x prime is congruent to x, y prime is congruent to y, so x prime, y prime is congruent to xy, right? We've already shown we can multiply congruences, and so x prime, y prime is in xy bar. Okay? They differ by an element of m. And so therefore this definition of multiplication is independent of the coset representative that we choose. So now we have a multiplication on our bar, and we have to show that it satisfies the distributive law and that what else? And then it has an identity. Okay. So for the distributive law, consider the coset given here, right? So we're multiplying x bar with the, or rather, we want to consider just this, so this expression all in terms of cosets, right? So we're multiplying a coset with a sum of two cosets, okay? So the first thing we can do is we know that in the sum, right, the sum of two cosets is the coset corresponding to the sum of the representatives. And then we have a product of two cosets, which is then the coset corresponding to the product of the representatives. Okay? Now we can use the distributive law on R to get that this is xy plus xz, and the coset representing that. And then we can break this up over addition, right? So this is xy bar plus xz bar, which is, and then we know that this product is equal to x bar y bar plus, and then this is x bar z bar. Okay. Finally, if we look at, rather I should use 1 times x bar is the coset corresponding to 1 times x, but 1 times x is just x, so this is x bar, showing that, well, we're missing some steps, but they're literally just like the simple calculations of the same type, right? So we would multiply on the right as well. So this shows that 1 bar is a multiplicative identity. Thus, oopsies. Thus, our bar has a ring structure. Okay. So that's it for this video. Hope you enjoyed, and I hope you watch the next one.